Hi, my name is Kiran Baburaj. Whether you are a computer science enthusiast or a math lover or just curious about how data is connected, this video will take you on a journey through the core concepts, properties, and real world applications of graphs. First, let's break down the core terminology. Graphs are made up of two fundamental components, vertices and edges. Vertices, these are the individual points or nodes in the graph. Think like a building block. Edges, these are the connections between the vertices. They represent the relationships or pathways. Further, the paths, a sequence of edges that connects one vertex to another. And a cycle, a special type of path that starts and ends at the same vertex. Okay, let's explore some key properties of graphs. Graphs come in many shapes and forms, each with unique properties. Here are some of the most important ones. First is directed and undirected. In a directed graph, edges have a direction, like one-way streets. In an undirected graph, edges are bidirectional, like two-way roads. Next is cyclic and acyclic. A cyclic graph contains cycles, while acyclic does not. Connected versus disconnected. In a connected graph, you can reach any vertex from any other vertex. In a disconnected graph, some vertices are isolated. Weighted versus unweighted. Weighted graphs assign values to edges like distances or cost, while unweighted graphs treat all edges equally. These properties define how graphs behave and are used in real-world scenarios. Okay, graphs are not just abstract concepts, they are everywhere. Here are some of the real-world applications. First is social networks. Graphs represent users as vertices and friendships as edges. Next is transportation systems. Maps use graphs to model routes and connections between the locations. Next is internet routing. Data packets travel through networks, models as graphs. And recommendation systems. Graphs help suggest products or content based on users' preferences and connections. So a graph consists of nodes and edges. But how do we store a graph in a memory? Well, we have two common ways, the adjacency matrix and adjacency list. First, we have the adjacency metric representation. This is a two-dimensional array where rows and columns represent the vertices. Each cell contains a value indicating whether an edge exists between two vertices, and in the case of weighted graphs, the weight of that edge. If an edge exists between A and B, we mark 1 at that position. Otherwise, it remains 0. This method is simple but consumes order of V square space, even for sparse graph with few edges. Adjacency matrices are great for dense graph where most vertices are connected. Next, we have the adjacency list, a more memory efficient way to store graph. Instead of using a matrix, we use an array where each index represents a vertex and stores a linked list of connected nodes. Here, each vertex stores only its direct neighbors, making it much more efficient for sparse graph. The space complexity is order of V plus E, which is better than the adjacency matrix for large graphs. So when should we use each representation? Use an adjacency matrix if the graph is dense, having many edges, and if you need fast edge lookups with order of 1 time complexity and memory is not a concern. And use an adjacency list if the graph is sparse, that is having fewer edges, and we need efficient memory usage with order of V plus E space complexity, and if we need to iterate through the neighbors frequently. So let's recap what we have learned. Graphs are foundation of many data structures. They have versatile applications across various fields. Understanding the graph is essential for mastering algorithms in computer science. They form the basis for advanced concepts like trees and networks. I hope you enjoyed the video. Don't forget to like and subscribe for more videos on DSA. Happy coding. Thank you.